And in fact, together with Kawai, Aoki, and other collaborators, I have been working on exact WKB analysis for differential equations, which is one of the typical examples of Resurgent analysis. And it's also related to the wall crossing phenomena. And today, I'd like to give a survey on our research on the exact WKB analysis for Painlev'e equations, that is typical second-order nonlinear differential equations. And after that, I will discuss our recent research on its generalization to discrete Painlev'e equations. But before discussing the Painlev'e equations, I would like to start with a brief review for the exact WKB analysis for Schrödinger equations, which is the origin of the exact WKB theory. So, section 1 is Schrödinger case. So, in fact, roughly speaking, this starts from 1980s, and mainly by Boros and Pan and Delaval, and also Japanese school, Aoki, Kawai, and me. And also, it is closely related to the recent research of the Riot under the name of spectral networks. So the research is done in a little different context, but it is very closely related to this analysis as well. Anyway, we are discussing a very simple equations like minus or eta minus square d square dx square or plus qx. Very simple equation here, like this second order linear ordinary differential equations. Here, eta is a large parameter. Usually we take positive eta, but sometimes we change the argument of eta as well. And for such a very simple equations, it is well known that there exists a so-called WKB solution of the form sin plus minus exponential of eta times plus 1 minus integral of square root q times infinite series in eta inverse, like eta to the power minus. For the sake of convenience, we add 1/2 here, c plus minus n of x, where n runs from 0 to infinity. So it is well known that this equation has this kind of formal or infinite series solutions. And in fact, this solution is, the construction is very simple in this case, but of course, this equation is usually divergent. So we usually, in this analysis, we consider the Borel sum of this WKB solution plus minus. So the definition is very simple. In fact, from this infinite series, we first define its inverse Laplace transform. Yeah, that is, this is a function of two variables. One is the independent variable of the x, and another is the developed variable of the large parameter eta. And this is by definition, we divide each coefficient by gamma factor like this. And exponential terms should be related to the translation, like x of square root q dx n to the power n minus 1/2. So this is the definition of the Borel transform, that is inverse Laplace transform. And using this Borel transform, we consider its Laplace integral, its Laplace transform, that is, we consider c plus minus b of xy dy. So this is the Borel sum, the definition of the Borel sum. We usually denote the capital letter of C. And usually the integration path is taken to be parallel to the positive real axis under the assumption that eta is positive. And the starting point is, if we denote this part by S of x, then the starting point is minus or plus Sx, minus or plus Sx to the infinity, to the point at infinity. So this is the definition of the Borel sum of WKB solution. And if we consider, instead of the infinite series, if we consider this Borel sum, then the so-called Stokes geometry should naturally appear. That is, to describe the region where this Borel sum becomes well defined. So the following natural geometric object appears, that is Stokes geometry. So in the case of the Schrödinger equations, anyway, yeah, the definition of the geometry is very classical. In fact, this geometry is defined by turning point and Stokes curve. And in the case of Schrödinger equation, the definition is very simple. Turning point is a zero of the potential Qx. This is a classical definition. And the Stokes curve is defined by imaginary part of the integral, that is, roughly speaking, this phase factor, that is, imaginary part of the integral of square root Qx from at some turning point to x should be equal to 0, where A is a turning point. So this is the definition of the Stokes curve when eta is positive. So when we change the argument to eta, then the definition of Stokes curve should be changed by adding eta here. But anyway, this is the definition of Stokes curve. So here I would like to give several simple examples. That is, example. So the simplest one is the Airy equation. That is the case where Qx is just a linear function x. So this is the Airy. So in this case, we have only one turning point at the origin, and the Stokes curve consists of three lines like this. This is the Stokes geometry for the Airy equation. And if we consider the quadratic polynomial like x squared minus e, here is a parameter, a positive constant like this, then we have two turning points at minus square root en plus square root e, and the Stokes curves run like this. So from a simple zero of the potential, three Stokes curves may emanate like this. So a little more complicated example, that is, if Qx is a rational function like x minus 1 over x, I have forgotten, x plus 1, x plus 2, and x minus 3 squared. If Qx is such a little complicated rational function, then in this case, we have two turning points at 0 and 1, yeah, like this, 0 and 1. And the potential has a singularity at minus 1 and minus 2 and 3, minus 1 and minus 2 and 3. And Stokes curves emanate from these two turning points, like, and this ends at one of these three singular points in this case. Like this. This is the picture of Stokes curves for this rational function. Anyway, and this is the definition of Stokes geometry. And in fact, if we consider the Borel sum of WKB solution, then the most fundamental fact is that so this is the first fact. So if we define the Stokes geometry by this, then the Borel sum of WKB solution becomes well defined in each Stokes region. That is, except on Stokes curves, the Borel sum of WKB solution becomes well defined. So that is, WKB solutions are Borel summable except on Stokes curves. So in this way, if we consider the Borel sum of WKB solution, yeah, Stokes curves play a very crucially important role. And the second fact is that, so in each Stokes region, Borel sum is well defined. But if we consider the analytic continuation of solutions or Borel sum of WKB solution across a Stokes curve, then a Stokes phenomenon occurs. So a Stokes phenomenon occurs. On each Stokes curve. For example, we explain by using a very simple example. That is, in the case of the Airy, for example. So we have this Stokes geometry, and each Borel sum of each WKB solution is well defined in these three regions. And if we consider the Borel sum in this region, for example, and if we consider its analytic continuation across this Stokes curve, that is positively variable axis, then we have the following connection formula. That is, if we normalize to discuss the concrete formula, we have to pay attention to the normalization of the solution for such a linear equation. But in this case, if we normalize WKB solution at the origin, that is at the turning point, then we find that, for example, on this Stokes curve, we have the following connection formula. That is, Borel sum in this region should be changed to C plus I times C minus in this new Stokes region. And C minus is unchanged, like this. The left-hand side denotes Borel sum in this region, that is, for imaginary part, x is negative. And the right-hand side denotes the Borel sum in the upper region, that is, for imaginary part, x is positive. So this is a connection formula on Stokes curve. And in fact, this kind of formula is, in a sense, very universal. In the case of Schrödinger equations, not only for the Airy equation, but for the other equations, on each Stokes curve, we have this kind of formula. So this is a very universal formula. And in the case of Schrödinger equations, so related to this connection formula, so sometimes usually we call this kind of formula connection formula. And related to this connection formula, I would like to give some remarks. That is, first, so if we use this kind of connection formula and combine this connection formula with the Stokes geometry, that is, if we combine Stokes geometry and this connection formula, then we can analyze the global behavior of solutions in the whole complex plane. That is global analysis. Of solutions becomes possible. For example, for such rational potentials, yeah, we can define the monodromic representation, yeah, very naturally, but such a monodromic can be computed if we use this Stokes geometry and this kind of connection formula. And this is one remark. And another remark is that, in fact, this connection formula is an immediate consequence of the Resurgent analysis. That is, this formula denoted by 1. Then 1 is induced by the analysis of the singularity of the Borel transform. That is, this formula induced by the so-called movable singularity of the Borel transform of WKB solution C plus minus dxy. So this means that if we consider the y-plane, so by the definition of the Borel sum, we have defined Sx by the integral of the square root q dx, okay? And by the definition of the Borel sum, yeah, the integration path for the Borel sum should be started by at minus Sx. But for example, if we consider the Borel transform of C plus in this situation, then this Borel transform also has a singularity at another point at Sx. Okay? And in fact, if we change, if we consider the analytic continuation in the x plane, that is, if we change x, moving from this region to this region, then this singularity moves also, of course. And in fact, on this Stokes curve, this singularity may meet the path of path of integration for the Borel sum. So this induces this kind of Stokes phenomenon. And in fact, in this case, we have the following explicit discontinuity formula of this Borel transform at y equals Sx. So then in fact, in this case, this must be equal to I times C minus d xy. So this is so in the terminology of the curve, yeah, this is nothing but the area derivative of C plus b. But anyway, we can prove this kind of Resurgent formula. So this kind of connection formula is an immediate consequence of this Resurgent formula. So this kind of formula, yeah, in fact, guarantees the Resurgence property of the WKB solution in this case. So this is one remark. Now, but one more important ingredient also exists for such Schrödinger equations. One more fact, yeah, fact 3. So here we consider the analytic continuation in the x plane, that is with respect to the independent variable of the differential equation. But next, at the next step, we want to consider the behavior with respect to the parameter that equation contains. For example, and if we consider the deformation with respect to the parameter, then we again encounter wall crossing phenomena. Phenomena occur when a parameter changes. When a parameter changes. This is the third ingredient of the analysis. So I'd like to explain this fact by using, again, a very simple example. So that is quadratic polynomial, that is. And if we, for example, if we consider the following potential, quadratic potential C minus x squared over 4, like this. So 4 is not so important, but anyway, we consider this kind of quadratic polynomial. Then, in this case, if C is positive, that is, argument C is 0, then in this case, again, we have two turning point at minus 2 times square root C and 2 times square root C. But for this special value of the parameter, these two turning points are connected by a Stokes curve like this. And if we change this parameter contained in the potential from, for example, imaginary part C is negative to imaginary part C is positive through the imaginary part of C is 0, then the configuration of Stokes curves changes from this and through this configuration, degenerate configuration, resulting configuration is like this. Like this, okay? So the pattern of the configuration change at this special value of C. In fact, in the so in the parameter space, that is in this case C plane, so the positive real axis in the C plane is nothing but a wall for this Schrödinger equations. And in fact, this is a real part of C. And if, in fact, if we consider the analytic continuation with respect to the parameter C crossing this wall in the parameter space from this region to this region, then another kind of Stokes phenomenon occurs. That is, for example, if we take the Borel sum in this region and normalize C plus again at x equal this turning point, that is the right side turning point 2 times square root C, then we have the following Borel crossing formula, that is, if the Borel sum in the region imaginary part C is negative, if we start this configuration, and if we change the parameter C from this region to this region, then the Borel sum should be changed to 1 plus exponential minus 2 pi I times C eta to the power minus 1/2 C plus for imaginary C is positive. So this is a Borel crossing formula. And in fact, this Borel crossing formula too is again has an interpretation in terms of the Borel transform. As a matter of fact, so this is a remark. This too is induced by, again, some singularities of the Borel transform. And in this case, this formula is induced by the so-called fixed singularity. Of the Borel transform C plus B of xy. That is, in this case, so again, we write the picture in the y plane. So again, the Borel sum should be taken, the integral from minus sx to the point at infinity along the path parallel to the positive real axis. And as I mentioned earlier, this Borel transform has a singularity at Sx. But in addition to this singularity, this Borel transform has another series of singularities, in fact, like this. These are other singularities, and in fact, in this case, this singularity at minus Sx plus 2 pi times c times m, where m runs the integer. And this kind of singularity does not move when the independent variable x varies. So in that sense, we call this kind of singularity a fixed singularity. And in fact, in this case, again, at each singular point of this kind, we have this kind of Resurgent formula. That is, this must be equal to minus 1 to the power n over 2n times c plus b. So this kind of Resurgent formula can be verified for the Borel transform of WKB solutions. And as a consequence of this kind of Resurgent formula, we have this kind of wall-crossing formula. So this is another ingredient of the exact WKB analysis for Schrödinger equations. And in fact, in this case, this 2 pi c, this 2 pi c is nothing but the contour integral of the square root of the potential. That is, this is nothing but 2 times square root q dx. In other words, this is the integral of square root qx along the contour like this. So in fact, this kind of fixed singularity appears related to this degenerate Stokes segment. And everything is controlled by such a contour integral of the square root of the potential. Anyway, in this way, in the case of Schrödinger equations, now everything is now understood by using this kind of Resurgent analysis. So this is an ingredient of the exact WKB theory for Schrödinger equations. So now we want to generalize this analysis to nonlinear equations. So in this case, Painlev'e. So this is a long introduction, but from here, the main part of my talk. So section 2, Painlev'e case. So again, we have discussed these Painlev'e equations since 1990s, and so Painlev'e equation is a typical second-order nonlinear ordinary differential equations, and we discussed Painlev'e equations after introducing a large parameter to discuss the exact WKB theory. And each equation have the following form, that is, the second derivative of the unknown function lambda with respect to the independent variable t should be equal to eta squared times some rational function of lambda t plus some rational function of lambda d lambda dt and t. And there are 6 Painlev'e equations. And the simplest one is P1. And P1 here is very easy to write. Yeah, in fact, P1 is nothing but eta squared 6 lambda squared plus 3. This is the famous first Painlev'e equation. And the second one is also very simple, P2. This is eta squared 2 times lambda cubic plus t lambda plus zeta. So zeta is a complex parameter. And we have another kind of another equation, P3, P4, P5, P6, and it becomes more and more complicated, so it's not so easy to write, so we omit the explicit form. But anyway, this is a part of the equations. And what instead of giving an explicit form, I would like to make some comments on the equations here. So in fact, Painlev'e equations is discovered by Painlev'e and his student Gambier by their trial of finding a very good equation that is here. The equation whose solution do not have a movable singular point. That is, this equation has a so-called Painlev'e property. That is, all movable means the singularity depending on the initial condition. But anyway, all movable singularities are just poles. So this is a very good property for solutions. And thanks to this Painlev'e property, every solution can be analytically continued in a unique way, except for the singularity of the equations. So in the case of P1 and P2, the singularity has only at that point at infinity. So thanks to this property, each solution of these two equations become meromorphic. Yeah. So in this way, this equation has a very good property, yeah, although this is nonlinear. And another important property for Painlev'e equations is the relation to the isomonodromic deformation. Isomonodromic deformation theory. So this means that so if we consider some appropriate second-order linear equations, minus d squared dx squared plus eta squared q of j x, and this potential contains x and independent variable of the Painlev'e t and the unknown function of the Painlev'e lambda, and also it's another parameter nu, which corresponds to the first derivative of lambda, and also eta. And in fact, if there exists some appropriate second-order linear equations, which here denoted by SLJ, and if we consider these linear equations, then the Painlev'e equation itself becomes isomonodromic condition. For SLJ. That is, the monodromy data of this linear equation becomes the first integral, or just a constant of this nonlinear equation. So in that sense, this nonlinear equation is related to this linear equations through isomonodromic deformation. So it's a very good example of the integrable system in one-dimensional case. And so having the exact WKB theory for Schrödinger equations, we would like to extend such a result to this nonlinear equation. This is our purpose. And in fact, in this case, in parallel to the case of linear equations, we can develop the exact WKB theory for this nonlinear equations as well. That is, we should start with a formal solution. So this is a nonlinear equation, so it's not so easy to construct formal solution. But for example, in this case, we have introduced a large parameter into the equation, eta like this. Then we can first, we can easily construct formal power series. Solution to that nonlinear equation. That is, we denote this by lambda alpha 0. This is nothing but a formal power series with respect to eta inverse. So anyway, if we assume a solution has this kind of expansion, then if we substitute this expansion into the equation, we can easily obtain each coefficient lambda 0, lambda 1, and so on. So in this way, we can easily obtain a formal power series solution. But from that form of the equation here, we easily find that the top order part lambda 0 should satisfy algebraic equation fj of lambda 0 tt is equal to 0. And higher order terms, lambda 1, lambda 2, and so on, are recursively determined. Once this top order term should be determined by this algebraic equation. So this is the first formal solution of the equation. But this solution is almost unique. So in fact, lambda 0 is determined by this algebraic equation. So this does not contain any free parameter. And higher order terms are recursively determined, and also these terms do not contain any free parameter. So it's a very, in a sense, rigid solution. And it is not sufficient to discuss this kind of formal power series solution, to discuss the Stokes phenomena, for example, for this nonlinear equation. And hence, second, we consider the so-called Torrance series solution of the Painlev'e equation. That is, roughly speaking, we denote this by T eta alpha. But roughly speaking, we add expression small correction to this formal power series solution to discuss the Stokes phenomena. That is, Torrance series solution starts with a formal power series solution lambda 0, and we add expression small correction like eta minus 1/2 alpha times lambda 1 plus eta minus 1/2 alpha square lambda 2 plus, and so on. These terms are all considered to be the expression small. Then, again, if we substitute this expansion into the equation, we easily find that. This second leading term, lambda 1, where lambda 1 should satisfy the so-called linearized equation of this nonlinear equation and this zero parameter solution, that is, or fresh derivative. That is, lambda 1 should satisfy d square dt square equal eta square, or maybe the derivative of fj with respect to lambda, and substituted lambda 0 t plus lower order term. this is a linearized equation. Linearized equation of Pj at this formal power series solution lambda 0. And we denote this linearized equation by delta Pj. Okay. Anyway, this is a linear equation for the unknown function lambda 1. And if we consider it a WKB solution of this linear equation, and as a lambda 1, yeah, we pick up such a WKB solution of this linearized equation. Then higher order terms, lambda 2, lambda 3, and so on, are again recursively determined. So hence, in this case also, yeah, lambda 0 and lambda 1 are both important parts of solutions. And as a matter of fact, reflecting this this simple property, in this case, Stokes geometry that is, again, this part becomes lambda 0, lambda are both divergent. So hence, we have to consider their Borel sums. But to describe the region where these Borel sums are well defined, we have to again introduce Stokes geometry for these solutions. But in this case, Stokes geometry, that is turning point and Stokes curves of this nonlinear equation Pj should be defined by turning point and Stokes curves of this linearized equation, delta Pj. This is a linear, second order linear equation, so the definition of the turning points and Stokes curves are well known. And hence, in this case, we define the Stokes geometry of the nonlinear equation by that of the linearized equation delta Pj. So again, for your reference, I try to write some picture. That is, for example, in the simplest case, that is in the case of P1. Okay. In the case of P1, then in this case, so this part becomes the potential of the linear equation. And hence, in the case of P1, dF1, d lambda, lambda 0, T becomes, in fact, F1 is nothing but quarter polynomial 6 lambda squared plus T. And hence, this is nothing but 12 times lambda 0, T plus higher order term, okay, lower order term. And this defines the Stokes geometry. And here, and in fact, this lambda 0 should satisfy this algebraic equation, 6 times lambda 0 squared plus T. And hence, roughly speaking, you take square root of this potential and define Stokes geometry. But in this case, the potential is defined in terms of this algebraic function lambda 0. And hence, it is better to write a picture of Stokes geometry not on the T-plane, but on the Riemann surface of this algebraic function lambda 0. And in this case, lambda 0 gives a very good global coordinate of the Riemann surface. That is, see, lambda 0 plane is nothing but a Riemann surface of lambda 0. And hence, we write a picture on the lambda 0 plane. And on the lambda 0 plane, again, in the case of P1, we have just one turning point at the origin. And 5 straight lines consist of Stokes curves, like this. This is a picture of Stokes geometry for P1 equation. And in a similar manner, in the case of P2, in the case of P2, again, in this case, df2 d lambda should be 6 times lambda 0 square plus t plus over the term like this. And here lambda 0 should with 2 times lambda 0 cubic plus t times lambda 0 plus theta is equal to 0. Okay. And hence again, we write a picture on the Riemann surface, in this case, lambda 0 plane. Okay. And for example, when zeta is positive, that is, the argument zeta is equal to 0, so we have a very fancy picture. That is, in this case, we have 3 turning points like this. And in this case, in the lambda 0 plane, yeah, singular points are point at infinity and the origin. And from each turning point, 5 Stokes curves emanate like P1. And in this case, roughly speaking, this is 3, and the other 2 are running like this. So this is the picture of Stokes curves for the second Painlev'e. It's a very fancy picture. Okay. And just like the case of the Schrödinger equations, we expect that Borel sum of lambda 0 and lambda 1 should be well defined in each Stokes region. In the case of P1, yeah, this in these 5 regions, 5 sectors, and in the case of P2, yeah, in these several regions. And this is correct. And in fact, in the case of Painlev'e, first, yeah, we discuss the Stokes phenomena. On the Stokes curve. Again, we take a simplest example, that is P1. P1. So in this case, we have 5 Stokes curve straight lines like this. Okay. And we consider the Borel sum, for example, in this region, the T eta alpha. And we consider it's a analytic continuation across this Stokes curve, positive real axis. Then, if we normalize, in this case, we have to pay attention to the normalization of the of lambda 1. So this is the WKB solution of the linear equation. Again, we have to pay some attention on the normalization of this WKB solution. But if we normalize this lambda 1 again at the origin, that is at the turning point, then in this case, for such a trans-series solution, we have the following connection formula. That is, we start with this solution for imaginary part lambda 0 is negative, that is in this region. And we consider its analytic continuation across this Stokes curve. Then the resulting solution becomes lambda of T eta alpha minus I over 2 times square root pi. This is an explicit formula for imaginary part lambda 0 is positive. This kind of shift occurs with the WKB solution or with this trans-series solution of the Painlev'e equation. So this is a typical Stokes phenomena for the case of Painlev'e equations. And also, we have the wall crossing formula for such nonlinear equations as well. So, wall crossing formula. And such wall crossing formula for Painlev'e equations was computed by our young collaborator, Iwaki, at Nagoya University. So again, yeah, P1 doesn't contain any parameter, so we have to discuss P2. And again, yeah, the simplest example, we discuss P2. Okay. And if we consider P2, for example, if now zeta is positive, so there are no degenerate, this is not a degenerate configuration. But for example, if we consider the case where argument zeta equals pi over 2, then in this case, the geometry becomes like this. And the origin is a singular point. And these Stokes curves are good, but these two turning points are connected like this. And simultaneously, these two turning points are also connected like this. So when argument zeta equals pi over 2, that is, if zeta is pure imaginary, then we encounter this kind of degenerate configuration, that is, two turning, or in this case, three turning points are connected by Stokes curves, like this. And hence, if we change the parameter zeta, that is, if we let argument zeta becomes greater than pi over 2, then the configuration, it's not so easy to write a picture in this case, but okay. But in this case, this degenerate configuration is resolved. And in fact, in this case, if argument zeta is greater than pi over 2, then this Stokes curves go like this. And instead, this is go like this. Okay? And in a similar manner, this goes like this, and this goes like this, and this goes like this, and this goes like this. This is one way of resolving this degenerate configuration. And of course, if argument zeta is smaller than 2 pi over 2, then this degenerate situation is resolved in a different manner. That is, we write in this case in a different manner. So this part becomes like this, and this goes like this. And this is go like this, and this go like this, and again this. So in this way, we have a different configuration when the parameter zeta changes across the imaginary axis like this. And under this situation, if we consider our trans-series solution, for example, say in this region, lambda theta alpha, and in a similar manner, lambda theta alpha, lambda theta alpha, and we take this particular turning point, we denote this particular turning point by tau here. Then, if we normalize lambda 1 at this particular turning point, t equals tau, then we have the following wall crossing formula. That is, if we start with lambda t eta alpha for argument zeta is smaller than 2 pi. That is, if we start with this trans-series solution for this in this region, and if we consider its analytic continuation across in the parameter space, that is in the zeta plane. So this constitutes the wall. So in the parameter space, this imaginary axis becomes a wall, and we consider analytic continuation across this wall. Okay. Then this transition solution is changed to lambda of T eta 1 plus e to the power 2 pi I zeta eta times alpha. This kind of Stokes phenomenon occurs for argument zeta is greater than pi over 2. So just like the case of the Schrödinger equations, almost a similar phenomena occurs with this kind of nonlinear equations as well. And in this case, I do not explain the proof for these formulas at all, but in the case of the Painlev'e equations, so this is just a remark. In the case of Painlev'e equations, so these explicit formulas are obtained by using the isomonodromy deformations theory. That is, these explicit formulas are obtained by using the isomonodromic deformation theory. To be more precise, that is, so as I explained earlier, so Painlev'e equations describe the isomonodromic property or condition for some appropriate linear equations. And hence, in fact, if we apply the exact WKB theory to such a linear equation, then we can compute the Stokes multipliers or monodromy data. That is, if we apply the exact WKB theory to the linear equations, then we can compute computation of the monodromy data for this kind of linear equations SLJ. Okay. And in fact, the Painlev'e equations is related to this isomonodromy deformation theory. So this monodromy data gives a first integral of solutions. That is, we can use here isomonodromic property for this particular solutions of equations. Then we can obtain some particular relations for these solutions. And if we write down this relation in an explicit manner, then we can obtain these formulas. This is a very rough sketch of the proof of these formulas. This gives a formula. So in this way, isomonodromic deformation theory is very important in deriving these very explicit formulas for translated solutions of Painlev'e equations. So this is a survey of the exact WKB theory for Painlev'e equations. And we have this. And from now, I would like to discuss the final subject of my talk, that is the final subject is its extension to discrete, to some discrete Painlev'e equations. And this is our recent trial with Narini Joshi at Sydney. But anyway. So for example, as a simple example, again, I would like to take the second Painlev'e, that is T lambda plus zeta. And we want to analyze the behavior of solutions with respect to this parameter in a more detailed way. Yeah, this is a very rough purpose. And in fact, in the case of Painlev'e equations, it is well known that, for example, the solutions of this second Painlev'e admits the so-called Becklund transformation. That is Becklund transformation. That is, in this case, it's a little complicated, but if we consider some transformation of the unknown function lambda by minus lambda minus zeta plus eta inverse over 2 over lambda square plus eta inverse d lambda dt plus t over 2. So if lambda is the solution of the second Painlev'e, and if we consider this kind of transformation, Becklund transformation, then this satisfies, it is well known that this satisfies the same equation as P2 with this parameter zeta being replaced just by eta inverse. That is, this is nothing but lambda shifted by zeta just by eta inverse. And in a similar manner, if we minus sign here, then this defines the inverse transform, and this gives a solution of the same equation with zeta being replaced by minus eta inverse. So in this way, in the case of Painlev'e, yeah, this kind of Becklund transformation should exist. So the behavior of solutions with respect to this parameter zeta is very well controlled by this Becklund transformation. And in fact, if we eliminate this first order term from these two Becklund transformations, we find that the solution of P2 should satisfy the so-called alternate dP1 equation, that is zeta plus eta inverse over 2 over lambda square plus, or not this one, zeta plus eta inverse over 2 plus over lambda plus sigma lambda plus zeta minus eta inverse over 2 over lambda plus sigma inverse lambda plus 2 times lambda square plus t should be equal to 0. So any solution of the second Painlev'e should satisfy this equation. So this is nothing but a difference equation with respect to the variable zeta, okay? With this kind of shift, okay? So in this case, in this sense, this difference or discrete Painlev'e equation is associated with this continuous Painlev'e equation P2. And we want to analyze the behavior of solutions of this discrete equations as well. For example, we like to discuss the Stokes phenomena for this discrete equation and so on. So the Stokes phenomena for such discrete equations are not so well investigated. So using this kind of WKB theory, from now on, I want to discuss the Stokes phenomena for this discrete Painlev'e equation. So this is a yeah, that's right, yeah. And in fact, in this case, the shift is just by very small shift, just by eta inverse. So in this sense, this difference equation is in a sense as equation of singular perturbation as well, yeah. So exact WKB theory should be valid also to this discrete equation, yeah. And in fact, but the shift is not so easy to handle. So to discuss this kind of difference equation, yeah, we first replace this shift operator, that is sigma lambda. This is nothing but the shift by eta inverse. But using Taylor expansion, we regard this operation like eta to the power minus 1 n and O n factorial dn d lambda d zeta n. Okay. We replace the shift by this infinite order differential operator, formal infinite order differential operator. Then this difference equation becomes an infinite order differential equation of the so-called WKB type. And in fact, we by the replacement of this, we can discuss again the formal solutions of this differential equation in a parallel way to the Schrödinger or Painlev'e case. But in fact, in this case, we should discuss not only this discrete equation, but we should discuss, of course, these two equations simultaneously. Yeah, in fact, solutions should satisfy both equations. So we have to, it's better to discuss both equations simultaneously. That is, we should discuss a system of differential equations. And in this case, in fact, first, we discuss this continuous or second Painlev'e. And also, instead of this difference equation, yeah, we use this Becquerel transformation equation, that is sigma lambda equal minus lambda minus zeta plus eta inverse over 2 lambda square plus eta inverse d lambda dt plus t over 2. And if we consider these two equations simultaneously, then of course we can obtain this difference equation as well. So from now on, we discuss a system of these two differential equations in both variables t and zeta. Of course, sigma lambda should be regarded as this infinite order differential operator. Now then, if we discuss this kind of system of differential equations, first, we can obtain easily formal power series solution. Very easily. So this is nothing but the formal power series solution of P2. That is lambda 0 t plus eta inverse lambda 1 t plus and so on with 2 times lambda 0 cubic plus t lambda 0 plus zeta should be equal to 0. So formal power series solution naturally satisfy both equations. So in this way, we have formal power series solutions of this system of differential equations. And furthermore, second, we have Toran-Series solution as well. Toran-Series solution. As a matter of fact, the form of the solution is the same. This is a starting with the formal power series solution. We add express a small correction like this. And the subleading part lambda 1 should satisfy the linearized equation of this system at this formal power series solution. And hence, in this case, this lambda 1, in this case, should be a function of two variables, t and zeta. And in fact, in this case, lambda 1 should be exponential of eta to the integral, in the sense of the one form, t minus 1 dt plus z minus 1 d zeta, like this. N times amplitude factor, eta to the power minus n lambda 1 n t zeta, and equal 0 to infinity. And where and in fact, in this case, t minus 1 is the same with the Toran-Series solution of the second Painlev'e. That is, t minus 1 is the square root of 6 times lambda 0 plus t. It's the same as the Toran-Series solution of the second Painlev'e. But this zeta part of the one form is, in this case, it's a very interesting factor. But cosine hyperbolic inverse of 8 times lambda 0 cubic minus zeta over zeta. This is the definition of the zeta part the transit solution. And in this way, if we use such a one form in the product space instead of just a function or just an integral in one variable, then we can construct this kind of transit solution of the system of nonlinear equations like this. And in fact, in particular, if we are interested in the behavior of solutions of these discrete equations, so for each fixed t, this gives a solution of this discrete equation. So lambda t zeta eta alpha gives a transitive solution of this discrete Painlev'e equation, alternative dp1. Okay. And in particular, if we are interested in the Stokes phenomena of these discrete equations, more importantly, the zeta part, that is this fact. Okay. And hence, for example, Stokes geometry of our discrete Painlev'e equation, alternate dp1, is defined in terms of this z minus 1. Okay. So in this way, again, Stokes geometry of the equation are naturally defined by this form of the transitive solution, that is z minus 1 part determines the Stokes geometry. And again, I write some picture here. So, for example, so in discussing the discrete equation, we have to fix t. So in this, today I would like to fix t just exponential pi I over 6. This has not a special meaning, but for example, yeah, I fix t at this point. Then again, Stokes geometry is defined in the Riemann surface of lambda 0. And in this case, in the lambda 0 plane, this is alternate of the zeta plane, that is Riemann surface. Of lambda 0, but in this case, very roughly speaking, we have 7 turning points. So 2 of them are very important. So 2 of them are turning points of the similar kind of P1. That is, we have 5 Stokes curves emanate like this from these 2 turning points. And in addition to this, to these 2 turning points, we have another turning points like this. And also, in this case, we have several crossing points of Stokes curves because we are discussing, in a sense, infinite order differential operator, so not a second order. And hence, there are several different kinds of Stokes curves, and hence we often encounter such kind of crossing points of Stokes curves. And in fact, in this case, related to these crossing points of Stokes curves, we have further 3 other turning points like this, and Stokes curves like this. So this is a picture of Stokes curves for this discrete Painlev'e equation, alternate dp1. And we are expecting in each region the Borel sum of formal power series solution and also transitive solution becomes well defined. And on each Stokes curve, some Stokes phenomena should occur. And we have not yet verified the Borel summability yet, but we have already computed the connection or connection formula for the Stokes phenomena, say, on several Stokes curves. And in fact, here we take 3 regions here, 1, 2, and 3. And these 3 Stokes regions are separated by these 2 Stokes curves. And here we would like to discuss the Stokes phenomena on these 2 Stokes curves. And say, for example, starting from this region 1, we take lambda our transitive solution T zeta eta alpha, and I would like to consider its analytic continuation across this Stokes curve. Okay, and to specify the meaning in this region 1, we denote the free parameter by just alpha sub 1. Okay, and after the analytic continuation in this Stokes region, we consider the transitive solution lambda T zeta eta alpha 2, and again in this region 3, we consider the transitive solution like this. Then our tentative result is the following. That is, at least on these 2 Stokes curves, we have the following Stokes phenomena. That is, this is a tentative connection formula for our discrete Painlev'e equation, alternate dp1 on these 2 Stokes curves. Okay. We denote this Stokes curve by S1 and this Stokes curve by S2. Then on S1 and S2. So again, we can obtain very explicit formulas. And in fact, on this Stokes curve S1, we have the following connection formula. That is alpha 2 and alpha 1. If this is a analytic continuation of this one, then alpha 2 and alpha 1 should be related by the following formula. That is 1 plus exponential 2 pi I zeta eta. This is the first explicit formula. And further, on S2, this is on S1. And on S2, if this is the analytic continuation of this one, then between alpha 2 and alpha 3, we have the following explicit formulas. Alpha 3 must be alpha 2 plus I over 2 times square root pi times exponential 2 pi I zeta eta. This is our tentative result. And very roughly speaking, the first formula is nothing but wall crossing formula. For the continuous Painlev'e 2, computed by Iwaki. And very roughly speaking, the second formula is just a variant of the connection formula for the first Painlev'e equation P1. In this case, the parameter zeta is contained, so the explicit form is a little different. So this kind of factor contains, but essentially this is the same connection formula as first Painlev'e equation. So in this way, so this is our tentative result. And I think it's very interesting that if we consider such a discrete equation with respect to the parameter, then we can, both types of formula appears. That is, wall crossing formula and also connection formula simultaneously appears when we discuss the deformation with respect to the parameter. So, and in fact, in deriving such kind of explicit formula, the most important point is that we discussed the system of differential equations, both equations. This is the most important point. So this is the final remark. Yeah. So this is the final remark. So when we discuss the discrete such discrete Painlev'e equations with respect to a parameter, so both connection formula and wall crossing formula appear simultaneously as just a connection at the same level of the connection formula simultaneously. This is the first remark. And the second remark is that the most important point is to discuss a system of differential equations. So we should not discuss each equation separately. So we should discuss a system of differential equations. And this is the second remark. And the third remark is that, so in this case, as I mentioned earlier, our discrete Painlev'e equation, ultimate dp1, is an infinite order differential operator, differential equation, in view of our replacement of the shift operator by infinite order differential operator. And hence, in this case, as I mentioned earlier, we have encountered several crossing points of Stokes curve and so on. And in fact, some turning points of our discrete Painlev'e equation is so-called virtual turning points. Virtual turning points peculiar to the higher order equations. So in this case, we are discussing infinite order differential equation. So hence, as reflecting this character of the equation, yeah, we encounter these kinds of virtual turning points as well. So this is a tentative result, but if we want to understand complete global structure of Stokes phenomena for such discrete Painlev'e equations, we have to discuss the structure of such virtual turning points. And perhaps, yeah, to discuss such virtual turning points, again, this second remark, that is, to discuss a system of differential equations is very important. So we have to not discuss just a discrete Painlev'e equation only, but we should discuss a system of differential equations. And this is what we are trying. Anyway, I think I should stop here.